This topic is over, under, around, and through a detailed comparison of QUIC and HTTP3 application mapping versus protocol encapsulation. But before I get into any of that, we just need to kind of dissuade or challenge some common myths or misinterpretations of what QUIC might be. So I'm going to go look around the room and assume people are familiar with TCP, if not experts in trying to understand what it's doing and how it's ruining their network or their day. So just quickly, QUIC is not TCP. It's similar to transport, a protocol. It offers similar kinds of services that TCP can do, but it's 100 times better, in my unbiased opinion. And also, you've probably heard that QUIC is a secure transport. It's not TLS. It borrows elements from TLS and designs. I'm not going to go into much of those details today. I'm going to focus on the QUIC specifics. Robin may go into them. I can't quite remember. But if you're that minded, again, we can talk later. You might have also heard that QUIC is just HTTP. You know, we're going to take H2 and stick it over UDP. It's not true. It's not HTTP. QUIC is a transport protocol. It can be used for lots of different purposes, and that's what I want to get into today. But it does borrow elements from HTTP2. So if you're familiar with that at all, the idea of multiplexing and streams, some of those will transfer over, but they're different, and those differences are what catch people out, but also make QUIC a lot more interesting and performant in certain kinds of networks. I've talked about HTTP2 and 3. They're not the same. They're very similar. They're not the same. And that is super important if you've seen the blog posts and announcements that went out about an hour ago about a CV and HTTP2 leading to DDoS attacks. I'm not going to talk about that today, but maybe next year. So, let the program committee know. We talked about the web. QUIC is not just the web over UDP. You might be familiar with QUIC from like the Google days of their experimentation going back 10 years or whatever, a long time ago. It's different. It came to the IETF standards land. I'm a co-chair in the QUIC working group, just one of many people in the chain of contributors to standardizing these things. And we paid attention to breaking apart the protocol so that it could be more modular. And I'll come into that in a few slides. So really what I want to say is QUIC is QUIC and HTTP3 is HTTP3. They're their own things. And they're similar to what you know, but where they're different, they're better. And where they're different, they'll catch you out and make you sad. And that's all I have to say today. Thank you. And the joke gets even better because this literally could have been all of the slides I could have made for various reasons. And again, I'll go into that in the coffee break. So let's get on to the real stuff. I've already mentioned this. QUIC is a secure transport protocol. What does that mean? Transport protocols transport things. Effectively, it's just IP addresses with a port number on them. If you put the port number in IP, you wouldn't need UDP at all. It would have just worked. Transport protocols offer other services like reliability or ordering. I'll come on to some of those. Traditionally, they didn't offer security. That's why TLS came along to add that. We're in a world now where things need to be secure and they need to be safe. They need to make the internet operate fairly. And in the kind of world we live in, where there's adversaries around that can do stuff, even if we would prefer them not to. And really, for this talk, what I want to make sure is you understand that QUIC is what you make it. Just a transport protocol on its own is rubbish. It's like a delivery truck with nothing in it. It can move around, but it doesn't provide any value to anyone. You need to load it up with the things that you're interested in, or your customers or your end users. Or you need to be able to go inside and understand why the package is busted because somebody dropped something. And I want to be able to give you some of the tools to understand where to start with that. I can't give you the answers, but I can help you on your way. And Robin's going to go into a lot more of the kind of deep technical aspects of those things too. So where do we start with all of this? I've talked about the IETF, the Internet Engineering Task Force, and the work we've done there to standardize things based on previous work. And a few years ago, the conference seems full of QUIC's coming, it's going to be done soon, we're going to start deploying it, et cetera, et cetera. And effectively, we start where we end, then that a lot of the work is done. We have standards now. I could probably spend 40 minutes talking about each of these specs in detail, if not just one of them, just going just full into it. And I don't want to. I'm going to have to do a really broad swathe and deep dive into one aspect to tell you about some of the new stuff that personally I find more interesting about using these protocols. But this is it. We have a landing page at quickwg.org. We have these RFCs. We've got a cool number. This is why we need to put the RFC number here, because RFC 9000 is QUIC version 1. Beyond that, we have RFC 8999, version independent properties of QUIC. That doesn't mean anything to anyone, but effectively it's a snazzy way to talk about what the kind of wire image of QUIC is that's independent of the version. RFC 9000 is version 1, but we expect there to be other versions. And if you've already peeked ahead to the next column at the bottom, we have QUIC version 2. It's different, but it's exactly the same. And that's as much as I can say without wasting too much time on it. But we have other things. Effectively, the core of QUIC, what it looks like on the wire, what it is, what services it provides, and how it does stuff, how we use bits of TLS to secure it, and how we detect loss, and how we do congestion control so we don't collapse the internet with those things. In addition to that, the protocol is really extensible. Because it's encrypted, the packets are protected. It means that the people in the path can't fiddle with them and break stuff as easily as they could with TCP. And so it makes extensions more viable, more interesting. And we've already got a few of these things. Most interesting of those is the datagram at the top. Again, just my opinion. There's more coming as well, but that one I will be going into more detail. And we've got these other documents like applicability and manageability. I think this group is probably going to be interested in those because they talk about how to use QUIC itself rather than what the details of QUIC are. Just this is effectively your API or your abstraction layer. These are the things you can take for granted of what it will provide, but the caveats in how you use those things. And again, especially the manageability. If you're an operator of a network or services where traffic's traversing, what kinds of things can you assume? What kinds of things shouldn't you assume? There's like lots of text there. It's maybe a bit terse, but at the point you get where you think, I need to be able to understand this better, those documents capture everything that the QUIC working group believes was important at the time. We're going to carry on learning. There's always new things that come around, but they're a good snapshot of what we think is useful. And then the last kind of group is H3 and QBAC. We standardized those in the QUIC working group, but they've moved back into the HTTP working group in the IETF. Effectively, there's a whole cluster of HTTP semantics, messages, request responses, and wire versions, so 1.1, 2, and 3, and again, another talk for another day. But let's get away from boring specs. We have to have the obligatory diagram comparing TCP, TLS, HTTP 1.1 and 2 to QUIC. I hate layer diagrams. They just lie. They're useless, in my opinion, but that's just me. I work on this stuff all the time. So if they help you, great. There you go. There's your diagram and whatever. But let's actually look into what some of this means. We don't need to compare it to TCP. It provides some of the stuff that TCP does, but it's better. So what does QUIC provide? Like, this is how I consider these things. I've mentioned already, but we have transport layer, the packets, the QUIC packets that are sent between clients and servers, just the model that there's a client and a server compared to peer-to-peer or whatever. Those things are all defined in the transport layer. I've mentioned congestion control, but there's flow control too. That's different. Again, can't go into that today. We have reliable streams and unreliable datagrams. Those are effectively the vesicles or the vehicles to carry application data. People who care about applications, that's all you need to know. As long as your library is not buggy or there's an interop issue, just assume everything's fine. But linked with that, kind of part of the puzzle pieces interlink, and they can be swapped out, and the image might change, but the overall shape doesn't. And these things effectively combine, but they're not coupled in many ways. And there's not clear interfaces either. So again, every analogy is broken, just like this puzzle. But next up, security, authentication, key exchange, packet protection, and then recovery, loss detection, and congestion control. And above that, we have this common layer application mapping. HTTP3 is an application mapping. It describes how the HTTP semantics I mentioned, how to send a request and get a response back, how it's reliable, how those things work, all depend on how you map that into the features of QUIC. And I'll come on to those in a little bit. So that's kind of what my world is. I've come to the SREcon for the first time. I don't know who the audience is. I haven't had much chance to mingle yet. So I kind of came up with 3 imaginary personas that you're maybe the person on the left, a happy person who just doesn't care and you don't want to know. Maybe it's going to speed up your website, and that's great because everything's faster. But maybe you are a user who just sees a random Chrome white page of doom that says like error, handshaking or something. I'm sure we've all seen that at one point or other where you boot up a laptop for the first time in 2 years and it says the time's wrong and there's an OCSP failure or something like that. Those kind of failures are really annoying and they're pretty hard to debug. And there's a whole other talk on that I did last year at a different conference going into those things. So I encourage maybe going and seeing that one if any of this piques your interest. Maybe in the middle column is people more like this room, people who operate networks or systems or have some need to fire up Wireshark or packet captures from every now and then because they're seeing weird stuff happening on their networks. The manageability draft I mentioned covers a lot of those things, and we'll go into some of it in the next few slides. Maybe you're the person who likes to build stuff, and again, we'll come on to that one. So we'll go back to the start again. With all that in mind, every QUIC connection will start with a handshake. We can have the whole sequence diagrams, and I'm not very good at drawing those, especially not with a trackpad, but we have a three-way TCP handshake and then another TLS handshake unless there's zero RTT, et cetera, et cetera. It doesn't matter for this talk. There's these sections of drafts that go into all of that. And Martin Thompson's gone into all of the really hardcore details of those things and go and watch those things. But what we do need to know is when things go wrong, what are we looking for? There's only 2 packets or 3 kind of packet types you really need to know, and you're kind of on a pathway to already solving some of those initial, I'm trying to connect to a server and nothing's happening. Like my client just sits there for 30 seconds and then closes the command line app or something. And then you realize you made a typo in the address and you're trying to like send random UDP packets to a different internet host or the wrong port. Those are the kinds of things that this level of debug is incredibly useful for and saves wasted time. So there's several packet types. QUIC has packets that are sent in UDP datagrams. We use UDP because it's great and it works. There's other transport protocols like HTTP that tried to define a new transport, like proper transport, and they just hit deployment issues because hardware or other systems didn't want to support them. So QUIC sits atop UDP, but it has its own packets that all need to fit entirely within a UDP datagram, removing a lot of the problems we have with packet fragmentation. So that's something we don't need to talk about, yay, except when it does happen. That's another talk. But what we have for the handshake that I think are the most important are initial packets. That doesn't mean the first packets, they're called initial. Like that's their name, not an adjective. And that's something that keeps coming back again and again. It's really annoying, and I wish we'd picked a different name, but hey-ho, you live with what you have. And a handshake packet, which is part of the handshake, which is also incredibly confusing. But if you just keep those 2 things in mind, like put them on the stack for the moment. Post-handshake, we've established a lot of what the client and the server need to know about each other, and then we can effectively amortize that cost and go to these simpler short header packets, or short packets, or 1 RTT packets. They effectively, they just contain some opaque bytes at the start of them, and then encrypted or protected payload that you can't see. Within that packet itself, from all of these packets, to be frank, is something called QUIC frames. So just a type length value binary protocol that carries different frames for different purposes. I could go into all of them. I don't want to today, but I will be covering some of them. So if you're familiar with the idea of framing, because it's a common protocol design thing, great. If you're not, I'm sorry. I didn't want to spend too long on that bit. But specs are great until they're not. You can read an RFC time and again, and still not really understand it. And then you go and Google a thing and you read a blog post by somebody, or you find online resources like xargs.org, which has illustrated examples of just the TLS handshake, TLS 1.3, and compare it to TLS 1.2, or the QUIC handshake. These are brilliant because they're kind of canned examples of real traffic. And you can expand each element and dig down and see the hex dump of them and understand from more of the wire image format what's happening with nice explanations. And like one of these things is the transport parameters. If you're familiar with TLS at all, they have the idea of extensions in the client hello, the first message it sends, or the server hello, which is the response it sends back. But one of these that's super important is something called QUIC transport parameters that communicate the capabilities of the endpoint. It's kind of a unilateral declaration of this is me and this is what I can do. The text is maybe too small or blurry to see here, but they control facets of the connection like payload sizes, boring, how much data you're willing to send. So as soon as you've done a handshake, how many bytes can the peer send you? You might be a tiny little IoT device with only like 4K of RAM. You can't support 64K of QUIC data just for one connection. So you might want to constrain things in that dimension. And some of the ones on the bottom relate to streams. I've created a follow-along example. These are done using just a simple command line client and server from the Cloudflare's quiche implementation of QUIC. If you want to follow along, great. If not, don't bother. It's fine. I'll go into enough detail that you can do this stuff. Again, a lot of these images are probably too small to make out exactly. I'll provide pointers to the key bits. But if you're familiar with Wireshark, this kind of trace is great. We can see the protocols being dissected in the protocol column and everything says QUIC, yay. But to actually make that work, you need a version of Wireshark that's 3.4 onwards. There was a time where that was like super new and really hard. These days, it should be a lot more common. You should just be able to fire up, download, install, fire up, and if you've got a PCAP with these things, see the traffic. But importantly, in this example, this is just a PCAP. This isn't a PCAP with some special encryption keys embedded in it or alongside as a sidecar or anything. This is effectively what the wire sees. So it's able to detect its QUIC. We've said it's a secure transport thing to protect it, and yet we're able to deep dive into some of these packets. We can identify their type and some of the things that are in them. So they're integrity protected, but in a way that's kind of known to everyone. So if you're smart enough to dissect QUIC, you can see what's happening. But if you're not, it just looks like random UDP. And there's reasons for that. Again, too boring to go into. But just looking at this initial packet I mentioned already, the client initial contains parts of the TLS handshake or the full handshake, however you might want to look at it. We have this client hello that's in there. We have something called an ALPN or an extension called ALPN that's in there. We have the transport parameters I've already mentioned, and in this case, this is the QUIC client's default parameters. So they're different than the ones maybe in the Xorgs example. There's one there called max idle timeout. That's a super useful feature. The endpoints can both declare an idle timeout. In this case, this is like 30 seconds or 30,000 milliseconds. The server could say, my idle timeout's 15 seconds. They both agree the minimum of that, and when that timeout expires without any traffic that would reset the idle timer, they can both just walk away. So there's no kind of explicit close that's needed. And that's just one example of something I think that's fun. And this ALPN thing, application layer protocol negotiation. We might be familiar with a world where if you had an application protocol like HTTP, you would pick a port number, port 80 or port 443, depending if it's in plain text or encrypted. But a while ago, we realized, wouldn't it be nicer if we just had one port for everything? We could share one port, a bit like server name indication does, that we can advertise the kinds of protocols we would like to speak. And the server would respond with an answer. So the client sends a list of these things. There's a big registry of them all. In this example, it's a little old. It's got effectively this, at the top of that list, the H3 string, which is the formal identifier for HTTP3, but then H3-29. Effectively, these are older versions. So you're able to quite easily, say if you're doing a stage rollout of a new protocol, negotiate and match and pick the version you both can speak. This was like super useful while we were developing QUIC over the years. Not so much now, you'll see less of this, but as new other application protocols come out over QUIC, they'll be following a similar kind of strategy for that. In the return direction, if we go on to the next packet, packet 2, we've got the server initial. Same QUIC initial packet type, but it's coming from the server. It's got a server hello in it, and it's got this handshake packet. And at the bottom, you probably can't see, but it's where that orange box is, it says secret's not available. And that's the bit we really want to see, because the client advertised a whole list of HTTP versions it wanted to speak, and the server would respond to one in that. And then you would know as an observer what the two endpoints were speaking. But because the secrets weren't available, we weren't able to undo QUIC's packet protection. And we're sad. So kind of taking a step back slightly, keys or endpoint logging are needed to see the full picture of what's happening with QUIC header. If you're familiar with this at all, there's like environment variable SSL keylog file. Many, not all implementations will obey that. If you, launch Google Chrome from your command line and pass that environment variable, just give it a file name, visit your bank, and then leave, you'll see there's a whole load of stuff in there about keys. If you pass the link to that file into Wireshark, it'll be able to then just decrypt the traffic. And it can do it live as well. It's pretty useful, pretty dangerous, because I don't want to know your banking details. But if you can maybe have an issue with QUIC, and you can constrain that down to a minimum viable reproduction that's safe, this is a really useful thing. But it only gives one picture of what happened on the wire. Sometimes you want to know, like, why an endpoint made a choice. Or you need to know things like congestion control, for example, is a sender-driven aspect of transport protocols, not just QUIC, TCP too. And because it's sender-driven, you effectively see the outcome of a chain of decision-making on runtime monitoring that every connection is doing. And you just see the outcome of that in this, effectively the size of packets or the number of packets being sent within any time quantum. And that's not very good if you're trying to debug what's going wrong with your congestion controller. So endpoint logging, I don't need to tell you how good logging is or how bad it is, but it's something that's useful, structured logging especially. And during QUIC's development, Robin came up with QLog, a standardized form of logging. And over the years, more and more implementations picked that up, and we adopted it into the QUIC working group, and we're trying to finish standardizing it. Logging format on its own is useless. Having the tooling to analyze that is what we want. There's something called QViz, a browser tool. Robin's going to go into that a lot more. Or, for me, what I've done is build my own library that can both serialize and deserialize QLog. And I've built my own tooling, which I would have loved to have open source by now, but we're all busy and timing it's not great, but look out for that one. It complements, it basically copies what QViz does already, but it can run offline and dump like charts and all sorts of stuff that personally I found useful. And what I would love is to make this more open to get feedback about what kind of tooling or enhancements we could add to those things. So Robin's going to talk about QLog. I'm going to talk about decrypted Wireshark. I've already talked about how you can do this in TLS. That link gives you way more details than I did. But we can now see the internals of the server handshake, have this thing called encrypted extensions. Those are the TLS extensions, but they were encrypted. It's like, does what it says on the tin. And we can see that there's an ALPN now. The server, in this case, selected HTTP 3. And post-handshake, if we kind of zoom back out to all of the other packets being presented here, we start to see inside. You can see from like the 5th packet down, the protocol changes now from QUIC. Remember, they all said QUIC before. Now it says HTTP 3. The dissector, as of maybe the last month or so, they've landed mainline support for full dissection of HTTP 3, including this QPAC thing that you would have seen at the start, which is great because we can see where the arrows are pointing, that there's a GET request there. That's on the right-hand side, get/index.html. But before that, we've got these things called stream and headers. What are they? They're the frames. The stream is the QUIC layer framing, and the headers is the HTTP layer framing. So we now have 2 layers of framing, which is incredibly confusing because they're both called frames. Then coming back, we have the response to that request. This is just a dummy, server running on my local host. So there isn't a file called index.html there. So instead I get a 404 not found response, and there is some payload data. I can't remember what that was in this case. I think it just said like, sucks to be you, or something like that. But that's carried in the data frame. So that's that. Now, quite often, as I mentioned, you could be anyone going, something broke and I don't know why. Could be me. It happens all the time. Could be my friends, colleagues, customers, et cetera, et cetera. And so one of the other frames that's really good to look out for, if you don't care about the handshake, if that bit worked and you see all of these things in the middle, for any trace that's worth anything that isn't a trivial example, it'll be megabytes, gigabytes maybe. But you just scroll to the end, and at the end will probably be a connection close frame. These are explicit closes in QUIC land. They can be an application or transport layer. This kind of doesn't matter the difference. They will use an error code, and that error code is probably registered with IANA, or it's in the RFC and explains stuff. And in addition to that, if it's an application level error, you'll have a reason phrase, which might contain the string. So in this example, I've configured the client to do a stupid thing and not give enough stream credits to open one of these mandatory control streams that HTTP3 requires. And the servers detected this and closed the connection immediately with the reason error open the connection stream. There's no way that that H3 connection could live or function properly, so the safest thing is to close it out. And this is just one example, so that's that. So let's talk about QUIC a bit. Less Wireshark, more QUIC. The best thing about QUIC, from a lot of people I speak to, especially people who are more layer 4 oriented, is it has something called connection IDs. Back to Wireshark. You would have seen these, I glossed over them, but effectively each of these short packets has something called a DC ID, a destination connection ID. No, that's wrong. I can't remember. Robin's going to go into this. But effectively, you can just treat them like opaque bytes. In this case, in this example, the packets that go from the client to the server have this DCID 770, blah, blah, blah. And the servers have different ones. And those bytes can be anything. They're picked. They should be different per connection, but you could embed or encode, your server infrastructure and have some simple service that just looks at bytes in a stateless way and can direct packets to the correct place. So compared to TCP routing, which needs to be stateful and causes all sorts of problems and interesting blog posts from my colleagues at Cloudflare, QUIC actually simplifies stuff for them. It makes everything else more complicated, but this bit they love. And we also in the ITF have this draft, which is called load balancers, which tries to formalize that a bit more. If you might be somebody who'd like to have a third-party load balancer in front of your HTTP3 server, or to buy a physical box to put one somewhere, this would kind of formalize the relationship of what that connection ID schema is and how things are done and protected in a safe way that can't be reverse engineered. The second best thing, streams. I mentioned those a few times. QUIC streams, one of the superpowers. Compared to TCP, this is one of the key differences, that you have multiplexing and concurrency in TCP. This is what HTTP2 tried to add on top with its own framing thing, and it was fine, but because of the way that TCP works, being its own single reliable byte stream, if you had some packet loss, you were just stuck and you couldn't do anything, and that was terrible. With QUIC, we break it apart. We put the streaming down into the transport layer, and all of the streams kind of run independently, which is great until it's not great. But what they are is just a lightweight, ordered, reliable byte stream. You can imagine it like a QUIC connection is a ton of TCP connections with a shared fate and shared encryption, which is a really powerful abstraction. They can be anywhere between 0 and 2 to the 62 minus 1 bytes long. They can be created by either the client or the server. So if you had a use case where you needed clients to connect to something and be pushed data, QUIC can support that. I know TCP can too, but in other protocols, it's maybe not as good. They're flow controlled. Again, this is more about local resources. If you're on a constrained client or you're on a server on a shared infrastructure, you might just want to keep a lid on how much data you're willing to be sent at any one point in time, because you maybe have a slow server that's consuming data from that, for example. Streams can be terminated without breaking a connection. Again, super useful, or they can be requested to be terminated from the other peer. They're not globally ordered. This is the kind of constraint I mentioned earlier. If you ever need streams to coordinate, QUIC can't provide that for you. You need to do it at your application layer. And concurrency is great until it's not. And I would go and read those blog posts about DOS attacks in H2 that I mentioned. In HTTP3 and QUIC, the whole thing, the whole mechanism works completely differently to achieve a similar kind of goal. It's a lot better here, and it's complicated. So I'm not going to go into it. QUIC stream IDs and types. Unidirectional, bidirectional, effectively the bits in the ID determine the type. Boring. Applications they need to decide how streams are used. This is the transport service, but applications like HTTP3 or DNS over QUIC describe exactly how the concepts that they have, request and response in this case, use a single bidirectional stream to send a message and get one back. So HTTP3, if you remember my jigsaw piece, now it's the application on the top. It's, as we should probably know, HTTP is a request-response protocol. H3 is the application mapping. Client-initiated bidirectional streams are always used for request and response exchanges. So You send your GET, and you want the response to that GET to come back on the same logical ID, because if you don't know what the response is for. This is just great. But it's effectively a layer of violation immediately, because you now need to keep track of QUIC stream IDs, even though HTTP doesn't have the concept of them. And this layering violation is effectively the application mapping. Hence why the puzzle kind of interlinked. Unidirectional streams, HTTP doesn't really have that sense. You might have heard of server push. Yeah, great. But there's other things it's used for in HTTP3, controlled channels, which I kind of mentioned already as a way to break stuff, and a different framing layer. Too much text, let's have a look at an image quickly. We have UDP datagrams at the bottom. QUIC packets must be completely contained in a UDP datagram. QUIC frames must be completely contained within a QUIC packet, but you can have multiple frames per packet, more than 2. It could be any. I could only fit 2 on this image. Above that, you have this logical stream. As I said, stream can be like humongously long, but it's segmented or chopped up into frames. Stream frames contain an offset and a length. So within that, as you receive them, if you, say, lost the 3rd packet there that contained a stream frame, you wouldn't have the complete frame. You wouldn't be able to read it end to end. You would need to wait for a loss detection and retransmission to happen, but eventually it would come back. On top of that logical stream, then, you have HTTP3 frames. Those can be any length, too. It could be 1 frame for the whole string. It could be a frame that kind of spans 2.5 QUIC packets. It could be anything. This difference is really powerful. Compared to H2, it means frames can be a lot larger. You avoid some of the weird hacks that they had to put in to allow kind of super long headers, like 64K of cookies and stuff. That was crazy. And on top of that, you've got this meta layer again of HTTP requests and responses. And the other thing I mentioned, the 3rd best, the datagrams. Reliability, only reliable things are retransmitted in QUIC. In TCP, you could detect a loss and retransmit the packet that was lost. QUIC doesn't work that way. Packets are never retransmitted. Only the data within them is. And as a server or sender, you don't need to send exactly the same frame that was lost. You might say, I tried to send you like 3 bytes and you didn't receive them in that packet. I've got another 100 I'm going to send you. It's more efficient for me just to send a whole 103. And because of the abstractions of QUIC and streams, this just works. It's pretty sweet. But sometimes you're an application and you don't need reliability. If you think real-time streaming use cases, the classic, you want to be live, and if you lose a few packets, you're going to fall further and further behind that live edge if you're waiting for retransmissions of stuff that no one cares about anymore. So it's easier just to accept that they were lost and jump ahead. So the datagram extension gives us that capability in QUIC. Sure, you could have just used UDP to do that in the first place. So it's effectively restoring some of the functionality we didn't have initially in QUIC. That's how I like to look at it anyway. And again, as all frames, the datagram frame must fit entirely inside a QUIC packet. With all of that in mind, I can finally get to kind of the crux of what this talk was supposed to be about, which is tunneling and using protocols and how you might approach these things. HTTP, just nothing to do with QUIC. HTTP traditionally runs over TCP. Doesn't have to, it just needs a reliability aspect underneath it, but that's the most common. And there's a thing called the connect method in HTTP, which has been around for decades. The primary use case to be, you're in a corporate environment or an academic network or something, and you need to connect to your bank, but they have a proxy that wants to intermediate everything. Just make sure you're not going to go to some hacking website or whatever. So the connect method was invented as a way to effectively allow you to establish an end-to-end TLS session over a forward proxy over multiple transport connections. The way this works is effectively these days, you would use HTTPS to speak to your proxy, and then you would have a HTTPS connection end-to-end to the server. So that's what the padlocks are trying to show here. My slide's been ruined. I've given the next one away. But effectively, it's an end-to-end flow of stuff. And that's a powerful concept. It's not just in HTTP, it's how protocol tunneling works or whatever. But we spent all of this effort to put HTTP over UDP. We thought, why not put UDP over HTTP? And the ITS spun up the MASQUE working group to kind of manage all of that work in tandem with what QUIC was doing. And HTTP needs reliability. It doesn't have a notion of unreliable data. So first what we needed to do was take QUIC datagrams and describe how HTTP would even map to that at all, make sure the HTTP people were like super happy with that. And then we used that as a building block to describe extended connect for UDP. And what this allows us to do is associate a logical flow of atomic messages or datagrams with an HTTP request. And this is what it looks like. You effectively tell the proxy server who you want to connect to. It will try and open a socket to that thing. It needs to resolve it. If it can't resolve the IP address, reject the connect request. If you're not authorized to use the proxy because you should be a validated client, reject it. But if you're accepted, then, well, hey, you can go. And you can build via a proxy almost the same diagram, end-to-end flow of unreliable messages. And that allows you to do UDP as a tunneling protocol. And what that looks like, probably are familiar with every layer of encapsulation just breaks stuff. And so you do have MTU issues with this kind of approach. It shouldn't surprise anyone familiar with VPNs, et cetera. And a different way to look at it, again, using my diagrams of stacking, these things. We can do QUIC over QUIC now. Yay. And you can do nested tunneling. You can chain proxies, and you can have encryption within encryption. Yes, more MTU issues, but you could do QUIC over QUIC, and then that thing is HTTP3, and then you could do connect over that to go and speak to your bank. And this kind of thing is powering privacy proxies, which are a powerful way to abstract the end server not knowing who the client was, because they don't need to know by their IP address. And that's what that would look like, a bit 70s. So this is my final slide, basically trying to, well, it's not actually, that's a lie, unpacking, unwrapping all of this stuff. It's a secure transport. You need to negotiate an application layer protocol. There's some that are standardized. You can write your own. It's actually pretty easy, just like scribble it on a note, post-it note, and give it a label. That's all I would require for interop, and I just encourage people to do it. Importantly, without the keys or logs, you're not going to know where you've broken your thing. And especially if you're writing your own complicated application mapping, you're not going to have a dissector. So you probably do want some endpoint logging. And that's why we created and trying to figure out this structured logging that's super extensible to allow you to do that. And so going back to the slide with one more point. QUIC is QUIC, HTTP3 is HTTP3, and the power is yours to use it how you want. Thank you for your time.